Welcome back. In this video, we're going to sort out some of the basic properties of isosceles triangles. And we're going to talk in particular about the details of what it means to assert that triangles are congruent. So let's take a look at the theorem of the day. We're going to be working with isosceles. Remember, a triangle is an isosceles triangle if two sides are equal. Now, an equilateral triangle is a kind of isosceles triangle. It doesn't say at exactly two or more sides need to be equal to have isosceles triangles. The theorem is if the triangle is isosceles and we have these two sides equal, then the base angles corresponding to them are equal. Angle B and angle C will agree as well. So let's prove this. Now, we're going to do two proofs because they really work, they function at different levels of sophistication. In fact, one of them is going to break down into two. So really, we're going to be reasoning about three different proofs of this. So the first proof that we're going to look at is a basic congruence proof. And that is a proof that uses congruent triangles. Now, we only have one triangle in this picture, so it seems we cannot reason about congruent triangles. But we can get two triangles by simply cutting this one in half. And so what we're going to do here for our first proof is we're going to construct the midpoint of the segment BC. So let's let M be the midpoint of the segment BC. So M goes here. I'm just going to eyeball it. And then, of course, whenever we have M, we can construct the segment AM like this. And now we have two triangles. Now, you might say, hey, we have two right triangles. And indeed, we do have two right triangles. But it's not so easy to prove that this is a right angle. In fact, there's no obvious reason why that should be, well, okay. Maybe it is obvious. There's no immediate justification for that being a right angle. It looks like a right angle, but that is certainly not enough. So what we know is that BM and MC are equal in length. We know that because M is the midpoint of BC. So BM equals MC by definition of M, effectively, because M is chosen to be the midpoint of that segment, so it must divide it into two pieces. So by definition of M. The definition of M does not guarantee us that this is a right angle. It does not guarantee us that these two angles here are equal, even though all of that seems to follow, and does follow eventually. But the definition of M only immediately guarantees us that BM and MC are equal in length, because it's chosen to be the midpoint of that section, of that segment. Okay, what else do we get here? We know that AM is equal to AM, and I'm not even going to write that down because every segment is equal to itself in length. So what does that give us? That gives us the side condition for triangle congruence. So triangle ABM is congruent to triangle AMC by the side criterion. That's the side criterion of congruence. In other words, if the three sides of two triangles are equal, then the triangles are indeed congruent. Now, I want to remind you that a statement of triangle congruence, and similarly a statement of triangle similarity, is not merely a statement about two triangles, but is an ordered statement about the roles of their vertices. And it needs to be phrased carefully so that the corresponding vertices are linked together by the statement of congruence. Now, in this situation, AB and AC are equal to each other. BM and CM are equal to each other, and MA and MA are equal to each other. A corresponds to A as we switch these triangles, C corresponds to B, and M corresponds to M. That means that when we phrase the triangle congruence, we need to order the vertices to make that happen. And here I've intentionally ordered them wrong. So I need to order the vertices so that I'm making a claim in such a way that I'm making B correspond to C and M correspond to M there. It might seem pedantic, but it makes a big difference. If we're careful about this, then we can trust that whatever corresponds, we can trust that the order here, like for example, I can say angle BMA must equal angle CMA without even checking the figure because I'm just trusting in the order to instruct me. So, so we really need to be careful about the order in which we assert these triangle congruences because it's a different statement. And the original statement that I had that ABM and AMC were congruent was actually false. Okay, so this gives us the congruence. And now if triangles are congruent, then some people like to say CP, corresponding parts of congruent triangles are congruent. And if they're congruent, then they're the same in every respect. Corresponding parts will be equal. And so we can start deducing that the angles are equal. And what angles would we like to say equal? We can prove that these angles are equal. We can prove that these angles are equal. But the point here is to prove that these angles are equal. And so I'll say that is angle B equals angle C by congruence here. And then we're done because that was the point of the theorem, was to conclude that angle B equals angle C. So that's the first proof complete. And I just want to remind you that the ordering of the statement of congruence is significant here. It makes a difference. So the next proof that we want to look at is a slightly different version of a congruence proof. And it's one of the simplest proofs of geometry, but in a way, it's also one of my favorites because it's surprising. So let us return to the original figure and roll things back to where we began when we stated the theorem, which is that we have a triangle ABC and its isosceles, and AB equals AC. Now, AB equals AC and AC equals AB, of course, which is the same thing, and BC equals BC. And as I said at the beginning, we don't have two triangles, and so we can't state a triangle congruence fact. But actually, that's not true. We have one triangle, but we have 6 different ways of saying the triangle by ordering its vertices. That triangle there, that is triangle ABC, it's triangle ACB, it's triangle BAC, BCA, CAB, and CBA. It is all of those things. And in all of those different orderings of the vertices are playing different roles as first, second, or third. The point of that is that we can actually state a non-trivial congruence result between that triangle and itself using a different ordering of the vertices. And so, and we already have all the information we need in order to do so. So let's just say it. Triangle ABC is congruent to triangle ACB. This seems like, well, yeah, of course it is. That's the same triangle, but no. It's the same triangle, but not in the same order. And so something significant is actually being stated here. What we're saying here is that when C corresponds to B and B corresponds to C, then after that reordering, it's still congruent to itself. So it's a non-trivial self-congruence of this thing corresponding to flipping it over this way. Now, every triangle congruence statement should be justified. If somebody just gives you a triangle congruence and doesn't give you a reason, then, well, you should never believe them, right? Why would this be the case? Well, it's simply side, side, side. And let's examine the 3 statements of side equality that are necessary in order to justify this triangle congruence. The first is the statement that AB is AC in length. That's one of the assumptions. The next is the statement that BC equals CB. That's the same segment. And the third side is the statement that AC equals AB, which is, again, a rephrasing of the hypothesis. So all of the necessary side equalities for this non-trivial self-symmetry are actually in the theorem hypothesis. And now, again, corresponding parts are equal, but the parts that correspond are now interesting because we have a non-trivial self-congruence of this triangle. And so we say, thus, the angle here, angle B, which is the angle of the second vertex in this statement, must equal angle C, which is the angle of the second vertex in this ordering of the triangle. And that's as desired. So this is a 2-line proof that doesn't even require the construction of the midpoint. It's an utter triviality, and there you go. Now, I was going to show you a transformations proof, but I think it's more important at this point to actually talk about how to do the congruence of this theorem, which is equally important and fits very nicely with this second proof. So what we're going to do, we're going to use the same figure, but we're going to say, what if instead of knowing that the sides are equal, what we actually know about the figure is that the angles are equal? Then does it follow that the thing is isosceles? So we're going to mix things up and look for the converse of this theorem. And well, since I brought it up, you can expect it probably is true. How could it not be? But let's phrase the thing carefully and then give a proof. So the theorem is, so if triangle ABC has angle B equal to angle C, then it also has AB equals AC. I'm not merely going to conclude that it's isosceles. I want to conclude that it's isosceles in a certain way, namely that AB equals AC. So if it has those angles equal, then it will have the isosceles characteristic in the sense that AB equals AC. And what we're going to do here is we're going to mimic the second proof that we did just a moment ago by giving a non-trivial self-symmetry of the triangle. So triangle ABC is congruent to triangle ACB but now I can't say side, side, side because I don't know side, 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 because the hypotheses of this theorem are about angles, and I really don't know that AB equals AC. It looks it in my diagram, but that doesn't count for anything. So I don't really know that the sides are equal. So do I even have justification here? Sure. What I have is angle, side, angle. So let's be clear about where are the angles and where are the sides. So what we have is angle, so to specify this completely, so angle ABC equals angle ACB, and BC equals CB, and angle BCA equals angle CBA. And maybe I'm being redundant here, but that really is the right way of phrasing angle, side, angle. Basically, I'm going to pick the angle at B and the angle at C. So ABC, ACB. They are the corresponding angles of these two ordered triangles. So ABC, just think about it in terms of the ordering of the symbols here, not instead of geometrically. ABC, ACB. That's the first claim. And then after the angle B, the side BC, and corresponding to the side CB. BC equals BC because that's the same segment. And then finally the angle C, which you get by saying BC and wrap around to A. BCA matches CBA. So BCA, CBA. That's, again, this angle equality. So the angle equality is effectively stated twice because it kind of has two roles here. It is the angle in the angle side angle claim. So angle side angle actually applies in a non-trivial way to give us a self-similarity, a self-congruence of this triangle. And after we get that congruence, then we have corresponding sides. AB, well, the side AB corresponds to the side AC because they line up, right? Again, thinking about symbol placement in the claim. So then side AB corresponds to side AC. And so they're equal. And so this shows us that the converse is also true, that if a triangle is, it has equal base angles, then it has two equal sides.